Let me share a couple of things. Okay. Yeah. So we spoke about the phase diagram for water, and these are the basic phase diagram that you'd find for water. Here you see that is why is it flickering? Okay. So this is the solid phase. This is the primary phase field of the solid water, and this is the liquid phase field, and this is the vapor phase field. And also we spoke about that's beyond a certain temperature. There is no distinct difference between what would be called a liquid phase and the vapor phase, and that's typically called the gaseous phase, where with the application of pressure only, you can't compress a gas to its liquid state, because in the gaseous phase, the interparticle sort of repulsions are so high that the attractive forces required to be present in a in a liquid phase is not enough for the gaseous phase to affect, and that's why they cannot be liquefied, and that typically what we call is the gaseous phase. Okay, what is generally called the gaseous phase, which can be made into a liquid phase, is actually vapor phase, to be very precise in scientific terms. And so below this critical temperature, you can have a water or liquid phase and a vapor phase equilibrium. In that, with the application of pressure or temperature, you can reach an equilibrium between two phases, that is the liquid phase and the vapor phase. But beyond the supercritical temperature and pressure, you won't be able to compress the gaseous phase and make liquid out of that. Anyway, so and the distinct thing about the water system is the slope of this curve. Okay, this equilibrium line, this two-phase equilibrium line, which exists between the solid state, solid phase, and the liquid phase, and that the slope is tilted towards the left, in the sense that a change in pressure or an increase in pressure actually decreases the melting point, and that's how it decreases the equilibrium between the solid state and the liquid phase to a lower temperature, right, which is very unique in water. Otherwise, you'd see in many systems this equilibrium line is going to be in a positive slope. It's going to be like that, which is very common. Okay, this one is not common, right? So in this system, it's a small common system, we can have a look as to how the equilibrium or the free energy of each of these phases differ or change when we talk about uh, keeping the temperature constant and trying and understand the various free energy components in a changing pressure environment. Okay, and likewise we can think about in a constant pressure environment how the free energy of each of these phases change with the changing temperature. Okay, these are the two aspects we'll talk today. So for that, let me come up with another slide, which is this one. Okay, can you tell me if you're able to see this? This is just an image. Uh, okay, let me. little bit of a problem. Okay, now if I have to share the content. Okay, can you see this now? People, can you see the image?
Yes,
Hello?
sir.
Yes, sir.
Okay. So let's say, let me just zoom into that. How do we do that? Control plus, right? So, okay, well, what you're trying to do is here, if you look at this part, this is just a cutout of the water system phase diagram, right? And here this is the solid liquid equilibrium line, this is the liquid vapor equilibrium line, and this is the solid vapor equilibrium line. Okay, and this is supposed to be the a triple point. It's not the critical point, it's a triple point. The critical point is not seen here, you know, that has to be beyond this temperature. All right, so in this, what we are trying to do is take a constant pressure slice. All right, I'm sorry, take a slice of at a pressure P1. All right, we keep the pressure P1, and then we draw a line like this, which is a dotted line that you find here. All right, and we see we like to see how the molar free energy of each of the phases change as we change temperature. So we have kind of reduced this whole system, whole phase diagram, uh, which is there between pressure and temperature, to something which is between temperature and free energy. And if you look at this one, just a little bit, okay. So this is where the temperature is changing, okay, and this is where the free energy is changing, okay. And of course we have to keep one thing constant, that is the pressure, and this pressure is kept constant here, and this pressure is actually this pressure here. We've kept this is the pressure. If this is the pressure, then you have to take a slice here, the slice of the phase diagram. So we are trying to see how the phase, the molar free energy of this phase and this phase and this phase are changing in a changing temperature situation at a pressure P1. Right? This is what is given here. Now, you can see here that it's typically what? It's typically the molar free energy versus temperature kind of um, uh, curve or the plot. And you have seen many such plots where we have plotted the free energy change with temperature. Okay, you can see that dg or del g by del t at constant pressure is simply, you know, the negative of entropy. Okay, so that's what is given here, and then that's how the slope here is kind of negative slope, right? And so since entropy is positive, minus s is going to be negative, right? Now, if you look at this, we need to essentially what you need to do is we need to identify at least 2 points in this P1 curve, P1 slice. We need to identify 2 points, and those two important points are when this pressure slice hits the solid liquid two-phase equilibrium and when it hits the liquid vapor two-phase equilibrium. All right, and we should be able to see that in this changing free energy versus temperature diagram. Okay, now if you look at it, this at P1, from temperature this to temperature this, solid is the most stable state. Why is that? Because this line runs through the primary phase field of the solid phase, right? And from A to C is the line where at this pressure, from temperature TA to TC, the primary phase field is liquid phase, So this constant pressure line actually runs through the primary phase field of liquid. All right. And then Tc to beyond, that the temperatures more than Tc, this constant pressure slice actually runs through the primary phase field of vapor. Okay, so if that were to be so, then what will be the molar free energy of the solid phase over this regime, over from here to about Ta? What will be the molar free energy of the solid phase? Because this is the primary phase field of the solid phase, the molar free energy of S, the solid phase, must be minimum from here to here over this temperature. And the molar free energy of the liquid state, liquid phase, is going to be minimum from A to C. Okay, that means the molar free energy of liquid phase is going to be lower than the molar free energy of the solid phase and the molar free energy of the vapor phase. Since the molar free energy of the liquid phase is the minimum, that's why this region is the primary phase field of the liquid phase. Likewise, when you go from temperatures from Tc and beyond, this is the primary phase of the vapor phase. That's why the molar free energy of the vapor phase is going to be the minimum compared to the liquid phase free energy or the solid phase molar free energy. All right. So all of these things have to be replicated here, to be seen here, to be reproduced here, with the fact that the nature of the free energy versus temperature kind of plot doesn't change, which means that the plots have to be like this. Has to be sloping downwards. It has to have a negative slope. So with that, how do you reproduce this? What I would do is, I would, since I am taking the same temperature scale here from here to here, I would simply draw verticals to identify points like A and C, and of course there's a point like B, which I had sort of alluded to in the last class, which is where this is the dotted line, all right? And this dotted line, which is actually the point B, where this dotted line hits the P1 slice, is actually an extension of the two-phase equilibrium between solid and vapor phase, which is this line. Okay, the equilibrium line between solid phase and the vapor phase is this line. This is a two-phase equilibrium line. It comes to this point, the triple point, where all three phases are in equilibrium. But then when this equilibrium line, two-phase equilibrium line, is extended into the primary phase field of the liquid phase, that's what we call as the metastable equilibrium between solid and vapor in the primary phase field of liquid. All right, so this is the point B, and that's also I draw a vertical here to denote the point B on the temperature line, which is TB. All right, now from here to here, I need that the solid phase free energy has got to be the minimum. So I draw the free energy curve of the solid phase, which is this.
Hello,
Right?
sir.
This is the free energy curve of the solid phase. All right. Likewise, I have to draw something which represents the molar free energy of the liquid phase. Okay, and such that the molar free energy of the liquid has to be the lowest between the points A and C. All right. So this is my A vertical, which is indicative of temperature TA, and this is my C vertical, which is the temperature indicative of temperature TC. All right. So within this phase, from here to here, I have to run the liquid phase molar free energy in such a way that this represents the minimum of all of those three. So this is my solid free energy phase. Okay. Now I draw the liquid free energy like this. Sorry, which is another sloping line like this. Okay, but it is drawn in such a way that the point A and C represent the minimum molar free energy, which is indicative of the liquid phase free energy from A to C. Likewise, I have to draw something from C, TC and beyond, where the molar free energy of vapor phase has to be minimum. At the same time, the molar free energy of vapor phase must also be a negative slope line. Okay, so this is the molar free energy line of vapor phase, which is like this, a little more steeper than liquid, than solid. Okay, but it still represents this line from C and beyond. And here it's a mistake that, they should have drawn the line as a dotted line here from here to here. Ordinarily, I draw all of those diagrams on the blackboard when I do on a face-to-face classes, but then since that's not possible here, I'm just looking at the book and sort of trying to explain things to you. So ideally, from C and beyond, this line should have been a dotted line saying that this is the free energy of the vapor, but then it is a higher free energy from this point to this point. But only at the point from TC and beyond is where the free energy of the vapor phase is becoming the minimum, and that's why it's given as a dark phase. So if you look at it, this line, this is the most minimum free energy. That's of the solid phase. That's why it is stable here. From here to here, this is the primary phase fill of the solid. From A to C, this is the most minimum. This belongs to the liquid phase free energy, and that's why from A to C, liquid is the most stable one, and you would see that A to C, liquid is the primary phase fill of the water system. And now C and beyond, primary phase fill should be on the vapor phase. That's why C and beyond, it's the minimum. All right. Now here, point B is represented also here. All right. How is it represented? Because in point B is an extension of the solid vapor phase two-phase equilibrium line, which goes to the triple point and runs into the primary phase field of liquid. So here, this line, this is the solid state line, solid state free energy line, and this is the vapor phase free energy line, and they interact with each other, or they sort of have an equilibrium, which is a metastable equilibrium at point B, which is represented, which is projected from this point to this point. Okay, there is a metastable equilibrium. Why is it a metastable equilibrium? Because here it's not the most minimum point. Lines would have the lowest free energy. Okay, the lowest free energy still would belong to the liquid phase. All right, but then they're slightly more energetic. But then these two phases have the same molar free energy at point B, which is represented here. All right, so this is about how the free energy, the molar free energy of each of the phases would be like in a changing temperature environment in this diagram. All right. Now talk about another diagram, which is we want to see the same molar free energies of each phases at pressure P2, and the unique point of pressure P2 that's taken here. Yeah.
Sir, basically at A and B and C, it represents the stability of different phases, no?
Absolutely, yeah. This diagram talks about the molar free energy of various phases, and from that you know what is the equilibrium free energies or equilibrium situations. That's depending on the free energy. When the free energy is the minimum, that phase is going to be stable. So that's it. In a way, it's a stability diagram for the water system and its constituent phases at the constant pressure P1.
Yes, sir.
All right, yeah. So like this, we want to explore the same thing in P2, and P2 is nothing but here it's very unique one in that it just intersects the triple point. That means the temperatures and the pressures that constitute the triple point. Here P2 is one of those. P2 is the pressure at the triple point. Okay, and how would that diagram look like? So I cannot show it right now here along with the main diagram, but then see what are the features of this main diagram at P2. P2 is where from this point to the point O, it's completely the solid phase. Okay, this is from temperature from here to TO, the solid phase is the primary phase fill. That means solid is the most stable one. And interestingly, after this point TO and beyond, you don't get the liquid phase here. What you get here is the vapor phase. So it's a solid to vapor direct transition when you go in the when you keep constant pressure P2 and then try and changing temperatures. All right. So in this situation, this is the point where this is the triple point, right? See, in this triple point, what is so nice about it? The triple point is where all the molar free energies of all the existing phases or three phases are same, because triple point is a point where three phases are in equilibrium, and here these three phases are the solid phase, the liquid phase, and the vapor phase. All right, when those three phases are in equilibrium, then their molar free energies are going to be crossing each other at this point. So we'll have to design or draw our free energy diagrams in at constant P2 and with the changing temperature in such a way that the solid, liquid, and vapor free energies crisscross each other. Whereas from this temperature to T, the solid free energy has to be minimum, and from TO and beyond, the vapor free energy has to be minimum. And in none of the cases, from here to here, it runs through the primary phase field of liquid phase. That's why the molar free energy of liquid phase in the diagram that we'll draw cannot have a minimum value, other than the fact that it touches at this point. All right, let's see how the figure looks like. It is as simple as it can be. All right, so what you do is you draw the solid phase. What is that? The molar free energy of the solid phase, which goes like this. The molar free energy of the vapor phase, which goes like this. And here it satisfies those two conditions, that from this temperature to TO, solid is the most minimum free energy phase. That's why it is in the primary phase field of the solid state, solid phase. And from TO to beyond, vapor phase is the least amount of free energy. That's why and since it is in the primary phase, the vapor phase. And in between, you'll have to draw a free energy diagram, free energy curve for the liquid phase, where in absolute terms it is between the solid's free energy number, vapor free energy number. That's why it is in the between. That's in absolute terms. But then it also has the same kind of dependence with temperature, like in a negative slope. But then in none of the cases, the free energy of the liquid phase is minimum, so that it will be the most stable one, other than the fact that there is only a critical point through which the free energy of the liquid phase passes, and this is the point where all the three phases are in equilibrium, as you can see from here. This is the point where all three phases are in equilibrium, and that's why degrees of freedom is 0 here. All right, so this is what represents the free energy diagram with changing temperature at constant P2. All right. Likewise, you can draw another simple diagram where it is P3, the constant pressure P3, and then how the free energy of each of these phases will change in a constant pressure and changing temperature environment. Okay. And you'd also see that from this to point E, it's only about solid phase, and from point E to beyond, this is about liquid phase. I'm sorry, vapor phase. And if you have to consider the metastable equilibrium between the solid phase and liquid phase, which is like this, and this propagates into the primary phase field of the vapor phase, having equilibrium between the solid and liquid state, and that is the metastable equilibrium line between solid and liquid, which runs into the primary phase field of the vapor phase. Okay, so if you have to reproduce that diagram of G versus T at P3, the diagram is going to be such that this from this point to this point solid has the minimum, and from this point to this point vapor has the minimum, and somewhere in between there will be a metastable representation of solid liquid equilibrium. Let's see what it does. Yeah, so this is what it is. So from here, this is the solid phase free energy. It goes like this. little limited slope. This is vapor phase free energy, a little higher slope. This is where from here to here, this is solid is stable. From here to here, the liquid is stable. And now there is this point F where you have equilibrium between the solid state and the liquid state, where this is the liquid free energy diagram. Okay, this is the liquid free energy, and this, the solid and the liquid crisscross each other at point F, which is representing of point here. All right. Likewise, you can also say that in the primary phase fill of the solid at P3, there is an extension of the liquid and vapor two-phase equilibrium line, which comes into the primary phase fill of the solid phase, which is at P3 represented by the point D, and this point D can be represented here. This is the point that's represented here, and this this temperature TD is where a metastable equilibrium between the liquid phase and the vapor phase will be shown, and that's what it is. You extend. This is the primary. I'm sorry, the free energy line of liquid phase. This is the free energy line of the vapor phase, and they are in equilibrium at point D, but that would still be a metastable equilibrium because this is the range, the primary phase field of the solid phase. All right. So likewise, if there is any single component phase diagram, all right, and you've been asked to find out what are the different free energy versus temperature diagrams at different pressures, you should be able to do that. Right. Likewise, we can have another situation where we can keep the temperature constant and see how the free energy changes with changing pressure. I would call that, let's take a temperature slice. These are the pressure slices. Okay, a different from the main phase diagram, you take a pressure slice here, here, and here. And if you have to take a temperature slice, you'll have to take a temperature slice here, because this is the temperature line, right? So you have to take a temperature slice here, or here, or or here, saying that how the pressure would change or how the free energy would change with changing pressure at this constant temperature that I have taken. I can take a line here, okay, and see how it changes, and I can take a line here and see how it can change. All right. So let's go to that one. So here, what we have done is, you have so this is the phase diagram of what? This is the phase diagram of same water, but then it is rotated 90 degrees. All right? Rotated 90 degrees. It was, in the other diagram, it was like this. It was 90 degree on the left. Now it is rotated on the positive side of 90. What we're trying to do here is that we're trying to take a temperature slice here, T1, T2, and T3. All right, and this one will keep the pressure changing and see how the free energy of each of these phases change at constant temperature T1. Let's go right away. So you likewise you can mark this T1, and you will see that with increase in pressure, this T1 from here to here runs through the vapor phase primary phase field. From G to I, it goes through the solid primary phase field, and from I and beyond, it goes through the liquid primary phase field. Okay, so that's how you do draw at T1 the free energy up here and the pressure changing here, and then you know that the nature of the curves would be slightly different than how the nature was between G and T. And G and T, it used to be like this, was a negative slope, and from between G and P, because del G by del P at constant temperature is volume. Volume is a positive quantity, and therefore the slope of this G and P line is going to be a positive number. That's why it's going to be somewhat like this, right? So with a positive slope, how do you represent the free energy of vapor phase, where from this temperature to this temperature is got to be the minimum? It is, I think, slightly overtly curved. You could draw something like this, but from here to here, and then it goes beyond. All right. So from here till about this temperature, we talked about this temperature. That's where the point G. The point G is where till about from this pressure to about pressure G. Vapor phase is the most stable one because that's the primary phase field. That's why it's free energy of the vapor phase from here to about point G. That's going to be the most minimum one. Likewise, from G to I, it's the free energy of the solid state that is to be minimum because this temperature slice moves from G to I pressure, and that runs through the primary phase field of the solid state. So the free energy of the solid phase, which is like this, okay, it has to go from G to I. That's the most minimum one. From G to I, no free energy would be lower than that of the solid phase. All right. And likewise, in a metastable equilibrium, which is point H, this point H is a metastable equilibrium between the vapor phase and the liquid phase, which you can find. This is point H. This is the metastable equilibrium between vapor phase and liquid phase. This is the two-phase equilibrium line, which a primary equilibrium after the triple point, it runs into the solid primary phase field with an equilibrium between vapor and liquid. That's why this line represents the metastable equilibrium. That's why it has got a second preference in free energy, and that's why it is given here. The second preference in free energy, meaning that the solid state would have the minimum free energy here, and the vapor phase and the liquid phase would have free energy curves crisscrossing each other. That means creating a metastable equilibrium at point H. All right. Likewise, from point I and beyond, point I is pressure I and beyond. That means pressure I and higher pressure. It's got to be the liquid phase, which is the most stable because from this point and here, it's the primary phase for the liquid phase. That's why you'll have to draw the curve of the liquid phase free energy, which goes like this, and from point I onwards, it has the most minimum values. Right. So this talks about the G versus P diagram, G versus P diagram at temperature T1 for the water system at temperature T1. Likewise, you can have the same things drawn for the T2. T2 is the most simple one because T2 is the temperature corresponding to the triple point here, and here it is completely the vapor phase primary phase field from here to about point TO, and from point TO to higher, okay, point TO, that is pressure TO, I'm sorry, PO, it's not temperature, it's pressure. So at T2, which is the triple point temperature, in this triple point temperature from lower pressure to pressure PO, the primary phase field is the vapor phase, and from pressure PO and beyond, the primary phase field is the liquid phase. All right, and it's only at PO and T2 where the solid phase, the liquid phase, or I'm sorry, the solid vapor phase and solid liquid phase and the liquid vapor phase, all those two-phase equilibriums come at this point and become as three-phase equilibrium point. But this is a point where all the free energies of these three phases shall meet, okay, with the positive slope. So come to temperature T2. Here it is as simple as that. Much like the diagram for G versus T in the earlier discussions, here it is G versus P. The only difference is that at G versus T, at triple point, the points were sloping downwards, and here it is going to be sloping upwards in the sense that it's a positive slope. And all of this free energy lines of vapor and the solid and liquid are going to be like this, where from PO and lower, it's the vapor phase which is more stable, and PO and higher, it's the liquid phase which is more stable, and PO is point where all three phase free energy diagrams meet, as simple as that, which is indicative of T2. Likewise, you can draw about T3. Okay, and T3 is here is slightly complicated in the sense that you have so many different temperature pressures that you can actually represent in the G versus P diagram, right? If you simply think it through, it is between the two important points, T3, this is T3, from lower pressure to about pressure K. It's the vapor phase field, which is most important, most stable, because this is in the primary phase field of the vapor phase. From PK, from PK onwards, PK and higher, right? It's the primary phase field of the liquid phase. Okay, so it's going to be between two, and it's vapor phase from here to here and liquid phase from here to here. After that, you can try and project all of those points where is crisscrosses between these three. That are there in the primary phase field itself. All right, let's go and see that. So this one is where this is point K. Point K is what we are talking about, right? So this is about point K. So first trace out the point K. That is PK that we have drawn a vertical. So anything less than PK, the vapor phase has to be most stable, and anything higher than PK, that's going to be the liquid phase, which is most stable. All right, so that's why I draw here the vapor phase like this and the liquid phase like this, and this sort of represents this. On top of that, we can project the point J and point L. Look at what point J and point L are. Point J is where in the primary phase field of the vapor phase, we have the solid and liquid, which is coming into the primary phase field of vapor. So it's a metastable equilibrium between solid and liquid, represented by point J, which is PJ, which is pressure J. So project this point onto the pressure line. So that is pressure J, and this pressure J is an equilibrium, should represent an equilibrium between the liquid phase and the solid phase. And this is the metastable equilibrium, right? And this point shall have higher free energy than a corresponding point on the same pressure of the vapor phase. And since the vapor phase line is like this, any point on this vapor phase line corresponding to point J for the vapor phase is going to be lower than this metastable point, which represents the free energy, molar free energy of either the solid or the liquid, or both, because at this point both are the same. All right. Likewise, we can talk about projecting the point L onto this diagram. And this point L is what? Point L is the PL. Okay, PL is simply projected here. And this PL is the metastable equilibrium between the vapor phase and the solid phase. Whereas this is the primary phase field of the liquid phase, which is what we are seeing here. The point, talk about point L. Point L, from point K onwards, that's PK onwards, liquid phase is the primary phase field. But at this point L, there is an equilibrium, that is metastable equilibrium between the solid phase and the vapor phase, which sort of is this equilibrium line, which beyond the critical triple point runs in a metastable manner into the primary phase for the liquid phase. For point T3, that's where it interacts with point L. Point L is PL, that's pressure L, and you can take L at PL and put it onto the last point, last diagram. Okay, this is the PL line, and this has to be something where a point should represent the free energy of the solid and the vapor phase in a manner that it is higher than the free energy of the liquid phase, because the liquid phase still has to be the most stable phase, and therefore it must have the minimum of free energy. All right, so this is what it is. We talked about how you can sort of draw how you can draw the different temperature and pressure slices from a single component phase diagram. And that's it. So I think we'll stop it here. We'll take questions if you have. We have talked long enough to sort of address some questions. Yeah.
Yes, sir.
या बोलिए क्या क्वेश्चन है? Yeah, any questions? Oh, let me stop the recording and then we'll take questions.